All right, welcome back to lecture 16 part 2, and we just looked at how the nearest neighbor algorithm works and what is the final hypothesis. And what we figured here is that this hypothesis set is where we can have all possible Voronoi tessellations on n data points, as you can see, right? Like all possible combinations of like all possibilities can be realized here, essentially, right? So what we figured was, and let me move on to the next slide, is that we have a VC dimension of like it's infinite. So you can like practically speaking fit any data set, right? And obviously we are getting an E in, which is so perfect, which is like 0. But because of this like VC dimension and going through the VC theory, we cannot really create a link between E in and E out. Right, so that's the dilemma that we're facing as of now. Because it's all great for the sample that we're working with, or the data that we're working with, but then we have to do something about the learning process that we've talked about so much. Now, one thing that like I might suspect is the example of the 5-year-old that we looked at earlier. They're obviously learning something based on similarity, right? They are somehow getting the relationship between whatever historical pictures they've looked at, and then they're trying to establish a relationship with a new unknown. So basically, they're answering questions about a new problem, right? So definitely there is a relationship between E in and E out in these similarity-based questions or similarity-based problems. But how is the question? So there is this theorem that shows that this nearest neighbor algorithm is indeed good. And the only thing here that we're missing, or the only thing here is that we cannot directly rely on the VC analysis, but we have to like take a different route. That's what we are doing here. Of course, we saw that this is doing good. This nearest neighbor is working really well with the data that's given to us. But we cannot directly say, given these issues here, that there is this relationship between E in and E out. All right. So what is that new theorem or this new path that we are taking? And so let me just like state this theorem. And this theorem says that my E out is at most equal to or less than, I would say, 2 times E out star. Now, what is this E out star? So I'm defining this E out star as the optimal error. So what is this like optimal E out? Okay, so this is my optimal E out. Okay, so first of all, this is what the theorem states, and along with certain accompanying criteria or condition is that we can say that this E out is less than or equal to 2 times the optimal E out with high probability, right? And sufficiently large n data set size. Okay, so this will stay here. So let's go back and see what do we need to establish. Like we need to establish learning is feasible. So we need to show that E out has some finite value because like E in is 0. So maybe E out has some small value, but how small? Like how small basically can E out get? So as I said, of course, we are establishing the feasibility of learning, but taking a different route rather than the VC analysis directly because of the issue that we just saw here. That's all we are doing here. So according to this theorem, we just like look at the statement. Of course, we're going to go through the proof. So if you just look at the statement, we are saying here that this E out is always less than or at most equal to 2 times this optimal E out. Okay, coming back to what is this optimal E out? That's the next question, right? So the best possible out of sample error. This is what this is. The best possible out of sample error. All right, this is the best that you can get for any given problem. So for a given problem, this is the best you can get. You cannot get better than this. That's what this is saying. So if you or maybe like in a very ideal scenario, you can think of it as the E out that's incurred by my F itself, right? The optimal way to classify every test point. Now, the question that comes to our mind is that we may not know what this optimal is, right? We can never know what this optimal is. So the only thing here we are doing is we are trying to establish this relationship between okay, this optimal classifier or this optimal classification exists, and the best we can do is that like we are approaching at most like this value, right? When of course n is sufficiently large with high probability. So in other words, my nearest neighbor contains, if you think about it, half the power of the entire data set. And you may use all the data available and reach E out optimal and then improve by a factor of 2, in other words, right? So that's the power of the nearest neighbor. So in other words, it's telling me that this is a powerful algorithm. This is an algorithm in which we can get a link to E out optimal in certain ways, and we'll see how, right? So basically, we're going to sketch a proof and finally get at this. So let's see how that is done, and let's begin with the proof, and let me write it on the next slide. All right, so the proof is we begin with the target function, which is f of x, and I am assuming that this is a probabilistic target function, just like we did in logistic regression, if I remember correctly. So let me sort of represent this by something that's pi. So this is like the convention whenever we are working with problems like these that we denoted by pi of x. So let's say this is my target function, pi of x, and this is nothing but, because this is probabilistic, right? This is nothing but the probability of observing y equals +1 given x. We have looked at this before. So this is like a probabilistic setting, and this is like observing +1 given x. That's all. All right. So now, what is my optimal classifier? If there was an optimal classifier, what would it do? Well, my optimal, I should write small, I think. Optimal classifier. Don't think we'll have enough space here, but that's fine. So what will my optimal classifier do? My optimal classifier is going to classify +1 if my pi x is greater than equal to half, and this is going to classify -1 if my pi of x is less than half. Usually the convention is to include this equal to with the +1. And why is that? Because if like pi of, and why, I mean like why is this definition for the optimal classifier, right? So if pi of x is greater than or equal to half, then that means that the chances of getting this +1 here are larger than a half, or like majority of the time the classification of x is +1, right? So basically if you say +1, then you agree. So you get an error of like 0 majority of the time. Conversely, or like the opposite, if you say -1, you will have a higher probability of error, because the probability of error in that case would be like 1 minus pi x, right? And so because the probability of pi of x here in this case is like greater than half, right? So this is how this is the optimal classification, and the reverse is also true. Okay, so this is my, and I would just like get rid of this so that the proof looks clear. So I don't want these things here. All right. Okay. So this is the definition of my optimal classifier. So let's see what is this optimal E out that I'm going to get when I have this like optimal classifier, right? So what is that probability of error? Because everything is like probabilistic here, right? So what is that probability of error that I'm going to get? And so I'm denoting it by star, remember? So my E out star x is going to be the probability of getting an error. So that can be like in turn denoted by 1 minus pi of x if my pi of x is greater than equal to half. True value was +1, but we classified it as -1. That's my probability of error. But this could also be pi of x if my pi of x is less than half. Pretty standard procedure. You say -1, and with the probability of pi x, it's going to be +1, right? So this is what my probability of error is going to be. And I'm going to, okay, let's first focus on this, and then I'm going to talk a little bit more about what this is exactly. So well, in either case, in either of these two situations, like this one or this one, like either of the two situations here, in this case, my E out optimal is the minimum of the two. Why? Like it's either like this or this. It's like the first line or the second line rather. And that's because when my pi of x is greater than half, like this one here, then 1 minus pi of x is going to be smaller. And then when it's pi x, then if my pi x is less than half, then my pi x is going to be smaller, right? So basically, to capture both scenarios, we can convert this to a more concise statement and say that my E out star of x is nothing but the minimum of my pi of x and 1 minus pi of x, right? Just like condensing them together. And one way to kind of denote this, like this E out star of x is eta of x. This is what you'll find in most of the textbooks. Even in our textbook, you'll find that. So that's why I'm like denoting it with eta of x. So we got an expression for optimal error, although we don't know what exactly this optimal error is. And the way we denote that, and let me maybe write it here, is that my optimal error is the average. Like, so basically it's going to be the integral of d of x px e out star x, right? So this is like the same line. Maybe I'll write it so that not to confuse anyone. I would just like try to fit in there. Yeah, it's E out star x. So basically the average of probability of error. That's what we are talking about when we are saying E out of x throughout this. All right. So we have the optimal classifier. We have the probability of error as well, right, for the optimal classifier. Now, we have to think more about the probability of error and what values can it take, right? So, and this is the, by the way, the optimal probability of error, right? So this is like the minimum of this or this. Now, there are certain assumptions that accompany this proof, and ideally speaking, these should be always stated when we are stating the theorem itself here, and I have kind of stated them in a certain way, but there is this like explicit assumptions that make our proof easier, and so I'm going to state them like now again. So the first assumption is that my pi of, so there are certain properties of pi of x that we usually assume when doing a mathematical proof, and so we are assuming that pi x is continuous. It's a continuous function. That's the first assumption. Optimal classifier may not be considered continuous, like it can take values +1, -1 depending on the values of pi of x, but we're assuming pi of x in itself is a continuous function. So that's the first assumption. The second assumption is about data generation, and I would say it's more like intuitive rather than like an assumption. So basically this assumption states that take any x, right? So any x in my n, like n data points, if I have an x, right? And let's say the nearest neighbor is like x1. So then it was classified as like, it's nearest to my x1, and maybe it was classified as like 1, right? And so what happens is that if like my n becomes like really large, my n is unusually large, or it's like approaching large. So what this says is this x1, this classification, whatever my nearest neighbor came up with, is essentially, so this implies that my nearest neighbor is going to approach that x. And this is going to happen simultaneously for all x. And why is this like an intuitive kind of an assumption? Like, let's say this is my x, right? And as I have like, I have like some data points, and then remember the Voronoi tessellations and all of that is happening. And then as I have like more and more data, like, so as n tends to infinity, there is this intuition that my nearest neighbor is going to approach the actual point, right? So that's what those are the two assumptions that we're going to work with, and then come back to out of sample error of nearest neighbor, which in other words is nothing but the probability of getting an error, right? So let's like come back to our proof with these assumptions. Let me just like separate this, and these are my assumptions, just so that we remember, right? Okay, so coming back to our proof, we are interested in getting the probability of error on some point x, right? And let us assume that this x has been classified by your nearest neighbor. So basically this is like probability that my nearest neighbor algorithm makes an error on x, right? So let's say this was classified as like some class 1. So the y value was 1, but actual y value was not the same, right? So we made an error there. So basically we are saying that we are getting the probability of, or not really, let's write it by p only. Okay, don't think we'll have enough. Yeah, so basically we're saying the probability of getting this when this wasn't the case, right? So there could be like two situations here. One, that the nearest neighbor said +1, and let's say this is a classification problem. And of course, that's what we've been assuming. So let's say nearest neighbor said +1, but actually it was a -1. And nearest neighbor said -1, but actually it was a +1, right? So this could be rewritten as, or like decomposed into those two cases when y of 1 is actually +1, when actually my y was -1, plus my y1 was -1, and this was actually +1. Okay, so if we think about these probabilities, and the definition of the pi was nothing but that this is like the probability, if you remember here, this pi of x was the probability of getting these y's as +1 or -1, depending on like the value of y given x, right? So we are going to utilize that definition and write these things, except that this is going to be pi for some x1, whatever my test point is, right? And this this is like the first one. The first one is going to be like both the cases condensed together, right? Because here I'm defining pi of x equals y equals +1 and a given x. And then the other case is going to be 1 minus pi of x, right? So this is going to be multiplied by 1 minus pi of x, plus this one is going to be 1 minus pi x for this one, this test point, and then the entire pi of x as it is. Now, if you remember our assumptions, right, the two assumptions that we have, so let's say we are generating more and more data and n is sufficiently large, and maybe write it here. So let us assume that n is indeed sufficiently large. So n is sufficiently large, then what happens? Well, what happens is that my x1 is going to converge to my x, whatever that x is. And also because pi is continuous, so if like x1 converges to x, then we can also say that my pi x1 converges to pi x in general, right? For sufficiently large n. So in other words, what we can say is that the probability of error for this point x is nothing but pi x 1 minus pi x, for the rest of the points will be the same, plus 1 minus pi x times pi x. All right, so if we just like rearrange terms, we're going to get 2 times pi x 1 minus pi x. Okay, and if you just look at it, what is this term here? This is the optimal error, is like not really, like not exactly, but if you remember, the optimal error is the minimum of one of these, right? So it was either this or this. Let me go back and see. This is how we defined the optimal error, right? So it was the minimum of like this or this. Now we have like both the terms in here, right? So basically what we are saying here is that the optimal error is the minimum of like one of those terms. So if one of the term is like eta x, this is how we were denoting it, then the other is less than 1 or equal to 1, right? Or we can write it here as like this is less than or equal to 2 times eta x, because that's what we use to denote it. And this is nothing but 2 times e out star X, like this was denoted by this. That's all I'm doing here. Now, this is an excellent result. This is a very powerful result, I would say, because this is saying that E out is at most 2 times the optimal error, right? And you can see there is this like bound that exists, and so we cannot go worse than this, right? And so nearest neighbor is at most a factor of 2 from the optimal, like, which is a remarkable result. I would say it's an excellent result. And you can see that the bound gets saturated when the optimal performance is good, and like when the optimal performance is bad, then you can get a factor of 1. So in both situations we are doing a good job, right? So this is like the final result, and this is like the proof of the theorem that my E out in the nearest neighbor is, I'm not going to get worse than this. All right, this is my optimal error. Okay, so with nearest neighbor, we will never know what is E out, but we know that it's small compared to my optimal. So what is the advantage of this result, rather? The advantage is that if optimal is good, you cannot be far from the actual optimal, right? Disadvantage is you cannot just look at E in and say something about E out like we did earlier, right? And so here is like a summary of the proof, right, with the assumptions and everything. And then this is the final result that we get. And this is indeed a good result. But like one question that might be coming to your mind is that, like, why is this considered a good algorithm, although it seems to be overfitting the data? And can we do something about it? So that's the question that we're going to answer in the next video.